Mistral have released Pixtral, an open source model that can take in text and images and give you a response in text. Pixtral can already interpret a wide variety of content, including newspapers, websites, and documents. But with fine-tuning, you can extend that capability to any custom dataset like medical or even satellite images. In this video, I'll explain how Pixtral works, how to use it to analyze images, and then how to improve performance on any custom dataset you have. If you're new to LLMs or multimodal models, you may find my code walkthrough useful, while if you're more advanced, I'll be sure to include a few tips to get the best performance out of your Pixtral fine-tuning. Let me start off with a description of the architecture for Pixtral, then I'll walk through a fine-tuning notebook, and I'll show you how to push it to hub, how to merge. We're going to train it with LoRA. I'll describe that later, and I'll show you how to merge the LoRA adapters and push the full model to hub. Then I'll show you how to inference that model using vLLM. I'll give you a one-click template you can use with RunPod. And then we'll finish off with one or two final tips on fine-tuning. Now, I've made videos on multimodal language models before. I made a video on Lava that you may wish to check out, and also one on Moondream, which is a very small multimodal model that I recommend if you want something extremely fast. So I want to focus on what the differences are with Pixtral versus those previous models. And the key attributes of Pixtral are, first of all, it's based on both a text and an image model. The text model is Mistral Nemo, which is a 12 billion parameter model. It's actually one of the strongest models for its size. Probably it is the strongest model for its size. And it combines a vision encoder to process the images. Now, typically models like Lava or Moondream, they'll use off-the-shelf image encoders like CLIP or SIGLIP. There actually are not that many vision encoders available, or at least there hasn't been all that much work being done to release open source versions recently. So it's interesting that Pixtral have developed their own custom and trained from scratch vision encoder, which is about 400 megabytes in size. So it's not that big relative to Mistral Nemo. And it supports images of any dimension, which I'll explain just in a second. Here's a simple sketch of what the full architecture looks like. So you have this vision encoder that takes in images, and then you have text that comes in. It gets converted into tokens, and then these tokens, which are subwords, get embedded, so they're converted into vectors in a high dimensional space. And then these vectors are fed in to Mistral Nemo's layers. So there are, I can't remember, probably more than 30 layers consisting of attention and feed forward. And then here on the vision side, we have vectors coming out of the vision encoder. There's one vector for every 16 by 16 patch of pixels in the image. And these go through an adapter, which is a single multi-layer perceptron. So that's the choice that Pixtral have gone for. In the earlier Lava models, this was just a linear layer, a simple linear layer. I think Moondream uses a multi-layer perceptron as well. So it's basically a linear layer with some kind of activation function, I think SILU or GELU, and then another linear layer. And that's the MLP sandwich. So the vectors go into this MLP sandwich, and then they come out here as transformed vectors, and they feed in the same way that the vectors representing subwords feed in. And based on all of these inputs, and you can intersperse an image, then text, then image, you're going to predict the next token. And with that next predicted token, you'll send that back around to the front and predict the next token, and so on. Now, if we dig in here on the vision encoder that Pixtral uses, I mentioned it's a custom encoder, so they've trained it from scratch. I expect that people will just rip off this encoder and use it because it probably is one of the best encoders compared to what's available through open source. In fact, I'd be surprised if Mistral don't themselves just make it available, because anyway, people probably will. So here's the vision encoder and how it works. It will take an image and it will split it into patches of 16 by 16 pixels. So here we have this teddy bear, and is it a teddy? It's a dog, cartoon dog. And I'm just showing some of the different patches of 16 by 16 pixels. By the way, this is probably a lot more than 16 pixels here, but just for illustrative purposes. So these tiles, each of these tiles represents an input vector. So basically all the pixel information, which means the pixel position within this tile, and then the RGB. So there'll be one scalar for the red value, one for the green value, and one for the blue value. And all that information for this tile here will go in to an embedding layer and be converted into a single vector representing this 16 by 16 patch. So for this picture, which has 4 patches, there will be 4 input vectors, one representing each patch here. And these will go into a vision transformer, which is again a multi-layer neural network that includes attention and feed-forward layers, and it will produce output embeddings. And these are going to be one each for each of the patches here. And what these embeddings represent is the meaning, essentially, of each of these patches. And the meaning of each of these patches then will be fed into the LLM here, where it will be combined with the meaning of the input text in order to help predict the next token there. So this is the Pixtral vision encoder, not too dissimilar from, say, the clip encoder or the SIGLIP encoder, except that it's capable of handling multiple dimensions of images, which I mentioned already. And the way Pixtral does this is best illustrated by this pseudo prompt I've put together. So say I want to ask a question about this image, and I ask, is the dog wearing glasses? And then I feed in the images. The way Pixtral will format this is it will put the question, is the dog wearing glasses? And then it will start to work across the patches. So we'll put in a patch here for the first, an image token here for the first patch, then another image token here. Then it will put in a break token to say that, right, we're moving down to the next row. So we put in another image token, bottom left, another image token, bottom right, and then break here because we're finished. Actually, there's an end of image token here that can go in here. And you can see the nice thing about this approach is it allows you to put in arbitrary shape images. So if this was a rectangle, say it was 3 across and 2 down, what you would do is just put in another IMG here, and you would put in another IMG right here. Now, this is in contrast to other approaches for vision encoders where you might decide to rescale. So if your image is not square, you would somehow rescale the image and force it to be square by basically squashing the horizontal dimension, for example. And then a third approach you could look at is if your image is too big, some vision encoders, what they'll do is they'll individually process the 4 patches here, and then they'll process a reduced resolution version of the entire image. So this is all kind of simplified with Pixtral in a nice way. They just use one image token for every 16 by 16. And then because they have this break syntax here, it's going to flexibly allow for images of different sizes. Just maybe to drive home my point and give a little more context here, in other image models, a pseudo prompt might, for example, just be, is the dog wearing glasses? And you would just put in one single token for the image like this. And so there would be no token kind of based information going into the prompt. It would all be contained in the tensors that are representing all of these image patches here. Whereas Pixtral decides to explicitly give some kind of token information on the image layout by putting these image tokens for the patches. So yeah, it results kind of in a longer formatted prompt. Although the tensor information is going to be roughly the same size and magnitude, you have a longer formatted prompt in Pixtral compared to an earlier approach like Lava or even Idefix. Idefix, it will just provide single tokens for the images. With that, we're ready to move on to do a demo of the notebook, a demo of the fine-tuning itself. So here I'm going to take a data set and fine-tune Pixtral to see if I can improve the performance on that test data set. And the way I'm going to do it is using a script from the Advanced Vision repo. So this is a Trellis private repository. You can purchase lifetime access to it if you go to trellis.com/advanced vision. It's the same repository that has scripts for fine-tuning Flux, which is an image diffusion model, and also for fine-tuning Idefix, Moondream, Lava. So I'm going to head to this repo. Those of you who have access, just go inside the fine-tune folder and then go inside Pixtral. And you'll see here, there's an IPYNB, which is a Jupyter notebook that you can upload to RunPod in order to do the fine-tuning. Now to run on RunPod, I'm going to want to start up an instance. And the instance I'm going to choose is one for fine-tuning. So I'll just go to the one-click. Now to run this notebook, I'm going to start up an instance in RunPod. You can start up an instance in VastAI or whatever service you're using. I'm going to pick a one-click template from the one-click LLMs repo. This is a public repo, and I've just added in. This is a template I'll talk about later for running inference. You don't want to run that for fine-tuning. Instead, you want to go to fine-tuning notebook setup, and we're going to run on run pod. So I'll find the one-click template here, and now I'm going to choose a GPU. If you're going to fine-tune Pixtral, you probably need a minimum, if you're not going to use quantization, you need a minimum of 48 gigabytes. This will allow me to fine-tune with a batch size of 1. If you want to fine-tune with a larger batch size, which sometimes can get better results because there's more smoothing across batches, then you want to use probably an A100. I'm going to go with the A40 just for now. Will I do that? No, let's actually go for the A100. So I'll go for an A100 here, which is definitely a bit more expensive. And you can see my template is selected. Make sure that the Start Jupyter Notebook button is selected. And then we'll go to My Pods. Now, just a tip, if you're not using my one-click template, make sure that you have enough volume on your disk. This is the disk that's attached to the instance. You want to have at least probably 50 gigabytes because the model is 30. Actually, you probably want at least 60 so you can store another copy. I would even do much more. I would do like 100 gigabytes just to be safe. In principle, your container can be small, like 10 gigabytes, as long as you're saving the weights to the volume, to the disk, which sometimes can be a bit finicky, and you just end up hacking it by putting a larger container if you see that the weights are being downloaded there. If you're using my script, they're going to be downloaded to the volume disk, so you're fine, but just, yeah. Sometimes when you use scripts off of GitHub, you find that they're not setting the caching directory for Hugging Face to be on the disk. And if you're not able to easily set it, then you might just make the container disk larger. It's a bit hacky, but can help. So here I've got my fine-tuning notebook, and I'm going to connect to Jupyter Lab. Then I'm going to upload that script I just showed you on from advanced fine-tuning here. So I'll head over to where I keep on my local computer my scripts under fine-tuning, and then I've got Pixtral, and then here I have Trellis Pixtral. Now, just a few notes on fine-tuning and Pixtral in general. If you go to the Mistral repository itself, you'll see that it's recommended to run using vLLM, and that is a good recommendation. I'm going to show you how to run on vLLM as well, but it won't allow you to do fine-tuning. And furthermore, the weights are not in a format that you're able to load with transformers, which is what we're going to use for fine-tuning. They're in this consolidated set of tensors format. So to fine-tune, we need to use a different version of the model, and that's available from Mistral community. It's called Pixtral 12b, and this model here can be loaded using transformers. So, for example, if you don't have access to my repository, you can always use this to load the model here, and then you can use Hugging Face documentation in order to do the fine-tuning, which I'll step through now. So I've uploaded this Pixtral notebook, and the first thing to do is to run installation. I'll increase my screen size a bit here so you can see. And I'm going to log in as well using Hugging Face, both so I can access the Mistral model, which is actually the Mistral model, the community one, it's not gated, but the original one is gated. It's gated, you can accept. But when you do that, you need to provide a Hugging Face token or log in. So actually, the real reason for me to log in here is because I'll want to push my finally fine-tuned model up to Hugging Face Hub. So I need to go and get a token, and I'll do so just by creating a write token, and we'll call it Video Pixtral. So I'll copy this, I'll delete it afterwards, and I'll input it here once I've got the fine-tuning setup done. One more thing is I'm going to enable fast weight transfers. You can see I've uploaded I've installed HF transfer. This is a Rust library that allows for much faster weight download speeds. So after I've logged in there, I'm going to run HF transfer. And yeah, I'm going to leave flash attention installed. If you're running on an A40 or on an A100, these are all supportive of flash attention too. They also support bfloat 16, which is how I'm going to load the model. If you're going to try run this in Colab, you'll have to run in float 16 and you'll have to comment out flash attention. Furthermore, you're not going to fit the model on a single T4 GPU on Colab without using quantization. So you'd have to uncomment this quantization here. and also pass the quantization config in to the model loading right here. I haven't verified this works in Colab, but in principle it should with quantization. So you can see here I've got my model ID set, and I'm going to do a few things for loading, which I've mentioned kind of, but I pass in the model ID, I set in the torch D type. So some of the weights are going to be stored in 32, in float 32. This will just ensure everything is loaded in brain float 16, which is a compact form of float 32 that has the same range, but it has a bit less precision. So on the Mantissa, it has a bit less accuracy. That means if you have a number like 2.166, it's going to simplify it to 2.16 maybe, but it's still going to keep the same exponent, which is say 2.166 times 10 to the power of 9. It's going to keep the 10 to the power of 9. So it uses less bits for the Mantissa. Now, for language models, we load a tokenizer. For image models, we load a processor, because we have to not just tokenize the text, we also have to process the image pixels and convert the 16 by 16 patches into vectors. So we have a processor in addition, or rather instead of a tokenizer. In fact, the tokenizer is in there, it's just wrapped within the processor. We're now downloading the shards, and we should have about 30 gigabytes to download. And I'm going to talk about templating, which is a bit of custom work here. But first, let me just mention the dataset. The dataset I'm going to use is Trellis chess pieces. You can check it out. It's a public dataset on Hugging Face, and it looks a bit like this. Let me just get out of the viewer and show you the model card. So it's a dataset with 48 training rows and 3 test rows. I think probably you need more data to get good results. As we'll see, you probably need 5 times this data. But essentially, I've put together this training set that contains pictures of my chess set at home. And yeah, maybe we'll go to the viewer. For every single row, there's an image, and then there's a brief caption. So here we have an image of a rook. And for that rook, I've got a caption here that says a single white rook. Now, I've generated these manually. You could potentially just take images and use a language model that's stronger, like Gemini Pro, to create some captions. But if your data is going to be very custom, that's probably going to start to break down, and you need to at least maybe do some manual inspection of the captions. And sorry, my screen is a bit small here, but you can just see the descriptions for each of these. If you want to create the data set and see how to push it to Hub, you can take a look at my Lava video. That's the multimodal video. And you can find the scripts here in Advanced Vision under Data Prep. So here you can see underneath the scripts, you're able to create a Hugging Face data set. You're able to create files for captions, and you can also do some conversions of HEIC to JPEG. I mean, you probably have images in JPEG or PNG, which is fine. So take a look at the Lava video if you want instructions on how to generate the dataset from your images and push those up to Hub. All right, so by now we have the model loaded, and I want to talk a bit about chat templating. So chat templating means preparing the prompt so that you have images and text interleaved and being sent in the correct format to get the right response back out from the language model. And you can see a naive way, which is also on the Hugging Face model card. You can see a naive way to do the chat templating. It's a manual form of chat templating where you literally take your prompt and you just put it together manually. So let's take a look at what's included in this prompt. So we have S in these conical braces. That's the beginning of sequence token. Then we have inst. This is technically not a token, it's a string. And this inst string stands for instruction. It's the start of instruction. And then we have describe the images, which is the prompt or the question. Then we have new line. Then we have 4 image tokens here, which are actually going to get replaced. We'll see that later by the image tokens for each patch, the new line image tokens for each patch. But actually these 4 image tokens currently just represent these 4 photographs from PicSum. And then we have /inst, which means end of instruction, and indicates to the model that now there should be an answer. So actually I've run everything above this, so I'm not going to rerun that because it will reload the model, but I can put all of this in the new cell. Take a quick look. Let's just see what the first image is here. All right, it's a dog. And let's run that. And this is just a demonstration of how to do a naive chat template. It's going to take a moment to run inference. We can check what the pods are doing. You can see that we're using 30% of memory. That's probably a little bit low because there's a lag in this updating. So it should, okay, and here we go. So image 1, a black dog with a glossy coat is sitting on a wooden floor. The dog is a focused expression. So you can see this is working well here in the naive form. But what we want to do is we would like to have a programmatic way to create these prompts such that we can feed in messages for the user, for the assistant, and those messages can contain both text and images. And so that's what we need to do by creating a chat template. So what I've done is created this chat template that allows us to format items for the user and also format items for the assistant. And it's capable of processing text items and image items. And you'll see here, look, it's putting in the S and the inst, and you'll see here it's putting in the close instruction right at the end. Now it's a bit painful to read through this, so it's easier if I just kind of demonstrate. But what I'm doing essentially is creating this Jinja template, chat template, and then I'm setting the chat template within the processor to be equal to this chat template above. Now you'll notice this is a nuance, but because there are these spaces here, which just make it easier for me to read this chat template, I'm going to replace those spaces with no space, because otherwise we're going to have these random spaces here that I don't actually want. So I'll run this cell to set up the chat template in the processor. There is none by default for Pixtral. And furthermore, I'm going to set a padding token. I'm just going to use the end of sequence token for padding. And with this done, I'm now able to apply that chat template to format any conversation. So here's a conversation where I pass in an image and a question, what do you see in the image? And I pass in an assistant message, and then I say, this is a chessboard with pieces. Now, by the way, you would never pass this in because you always finish with a user message. So for example, I can pass in a user message like this here and say something like, what pieces do you see? And I don't even need to pass in an image there because I've already passed in the image originally. So let's just as a demo see what that looks like. And here's the formatted text. So we've got beginning of instruction, image, what do you see in this image? End instruction, this is a chessboard of pieces. And then we've got another beginning of sequence token, inst, what pieces do you see? And then we've got the close sequence token. Now I can already see here there's one update I need to make to my example conversation. I'm not entirely sure, but I get slightly better performance when I put the image after the text in the user role. So I'm going to swap the order of that there. And there's one more tweak that I want to make here on the assistant message, which is we probably should include an end of sequence token when we have the end of the assistant's response. So once we get to the end of the assistant's response here, I'm just going to put in an end of sequence token like this. So let's rerun that. And now we have what I think we want. So beginning of sequence token, what do you see in this image? Image, close instruction, it's a chessboard with pieces, and end of sequence token, beginning of sequence token, what pieces do you see? And now it's ready to give a response. So yeah, I've set up this chat template. It's going to help us with the training. It's going to help us with inference as well. Next, we have a question of loading the dataset. So quite simply, we'll use dataset equals load dataset. We'll have the train and the eval set. If you want to inspect an image, you can do so. My images are quite large, so it'll take a second for the data set to load, the image to show. Here I'm just getting the object description of the image. It's 3000 by 4000. That's why it's quite a large image. Oops. And if you want to see that large image, you can just run that cell. It'll take a few moments for that resolution to download. Yeah, so here's the image, and you can see it's a picture of a bishop. Now I'm actually going to comment that out and run it again because I don't want to have too much data within my notebook for when I save it. So next we're going to evaluate performance on my test set. This is the 3 images that I've set up. We'll see if the model without any fine tuning is any good. So I'm going to run the model in evaluation mode, feed in each example in the data set the image, set the query. The query is just going to be a constant query, which I pass in up here. And the query is going to be, what do you see in the image? We'll see that a bit later down here. Here I'm displaying the image in reduced size just so it's faster to run. And then I'm passing in here the messages, which consist of a query and an image. Now you can add another image if you like, or you can add more text if you like. So this is flexible here. Then I format the prompt by passing it through the chat template. And I'm just doing it formatted here purely for the purpose of printing it out so I can see it. But then I actually format it here for the purpose of passing it in as inputs via the processor to the model generate function. And you can see the processor takes in text, which is the processed and formatted text, the images, which here is one image, but you can pass in an array of images like this here. And then it will return tensors, and it's going to use padding. Next, we will generate the output IDs with model generate, and then we will decode them, and we will print out that decoded result. So let's just run that definition, and now we'll run evaluation, passing in this question: what kind of chess pieces do you see? So here's the first image with a bishop and a knight, and prediction is 2 chess pieces. It's a bishop, and on the right it's a pawn. So it's not getting the right piece here. Possibly, it looks a bit too much like a pawn. The second question here: what chess pieces do you see? 2 chess pieces, a king and a pawn. So it's got the wrong quantity of chess pieces here. What you see here: a rook and a pawn. So yeah, it thinks again this is a pawn. So you can see it's not quite getting the answers right. And the question is, are we able to do any better? So now we're going to run fine-tuning on the training set to see if we can improve performance. And the first thing I'm going to do is set up a data collator. And what the data collator does is take the training data and set it up into the correct format. So for each example, for example, in examples, we're going to pick out the image. So I'm just picking out the image in the chess dataset row here. And I'm going to ask the same question in each case: what do you see here? And the answer that I'm going to run the back propagation and cross entropy loss on is going to be the caption, again provided in the dataset right here. And the way I'll pass in the messages is by passing in role user, content, text is the question, and then the image. I've put the image after the text. I think it's probably a little bit better. Probably will work before. And then I have the assistant, and I've got the content here, which is the answer. And this is what we're going to back propagate on. So we'll get the model to create answers, and we'll compare those answers to the actual answer that I have in my training data set. Now here you can see me using this chat template, and then I append the texts, append the images if there are multiple images, and then append the answer. And this basically gives me a set of texts and images that I can pass into the processor and get a batch back. And that batch is going to be passed into a forward pass through the model to generate some next token predictions. Now, just to comment that here I'm training on one conversation turn. That means there's one user message and there's one assistant message here. But you can also train on multi-turn. If I had a data set where there was not just a caption, but there was, say, first response, then first assistant response, then first user response. So that'd be 2 turns because it's user assistant. I could just set up a messages template here where I would have total turns, like 2 full turns or 4 role-based turns. And that would work fine as well for the purpose of this training. There's one rather subtle but important aspect to the training here, which is that, how best to explain this? Let's just take a look at how this will look when it's formatted. So let's look at what a typical prompt looks like when it's formatted, and then I'll explain what we are doing so that we only train on the assistant response and why that is a good thing to do. So if I go down here and I print my data set, so I'm just printing out the 0th row here, which has an image and then it has a caption. Now I want to inspect what this looks like when I format it with the chat template. So I'm going to take, looks like I'm going to take a small batch, so just 2 examples. I'm going to apply the data collator to that batch. So I'm going to set them up into the proper format, and then I'm going to print out information like the tokenized input IDs, but also print out the labels and the decoded inputs, which is going to be the text in prepared format. And here you can see the decoded inputs. and it will match a little what we talked about earlier. So we've got the beginning of sequence token. We have the instruction indicator. This is a string to say that the instruction is beginning. Then we have the instruction. Then we have a pile of these image tokens, right? Now, why do we have a pile of these image tokens? We'll come back to that. We have end of instruction, and then we have the answer here, which is a single white rook. So you can see this follows the format, but it's now got a pile of image tokens. And the reason is because every image we pass in is now being replaced by what I said it would be replaced by right here. So every image I pass in is now being replaced by an image token for every 16 by 16 patch. I should actually remove this because people will get confused. A break for every new line when we move to a new row of patches, and then more image tokens, 1, 2, and then end of image. And you can see that's exactly what we have here. We've got a ton of image tokens. Then we hit an image break. So here's the image break. A ton of image tokens, then an image break. So it's literally putting an image token for every patch. And then at the very end, you can see there's the end right here. There's the image end. And then we have the close of the instruction. So this is how everything is formatted. And it makes sense based on what I explained earlier. But if you just train like this, and by train, what I mean is if you get the model to predict every next token. So in other words, you're going to feed into the model. I mean, remember, this runs in parallel. So you can think of it literally as you feed in just this token and you get the model to predict the next token here, and you compare that to the actual. In parallel, you feed in the first two and you get the model to predict this token what, and you compare it to the actual. In parallel, you feed in these 4 first tokens and you get to predict this token and you compare it to the actual. And this is what happens when we do fine tuning or training. You can think of it like feeding in the first 1, the first 2, the first 3, all the way up to the first 2,000 tokens, if that's how long the sequence is, and comparing the next token. So the model is getting a ton of training on predicting what's mostly the user input, which is all of these tokens here. And then it's getting a tiny bit of training on the answer. So only for the last, let's say 4 or 5 token predictions is the model being compared to the actual on the user's answer, or rather on the model's answer here. So you get a ton of cross entropy loss comparison on all of this input, and then you only get a small amount of cross entropy loss comparison on the predicted tokens here by the assistant. And this ends up kind of being a problem for training because you really care about getting the answer right. You don't really want to train it on the question here. And if you train it on everything, there's going to be so much information coming from the cross entropy loss on this early part that it's going to be hard to see any signal from the back propagation on this assistant output part here. So actually what we want to do is we don't want the model to focus cross entropy loss on any predictions of the user tokens. We only want to train on the assistant's response, which is called completions only training. And the easiest way to do this is to set a 0 for the cross entropy loss position for every position in the user's response. So that's what I'm doing here with the labels. Basically, I'm creating a copy of the input tokens with the labels. And then for each of those labels that is in the that's in the user, I'm setting it to -100. And -100 means to ignore that for the purpose of cross entropy loss. So we're going to have a series of inputs. There will be a series of outputs predicted, and they're compared to the labels. But we're actually only going to compare to the labels for the assistant output towards the end. All of the earlier parts we're going to set as -100 so that we're ignoring cross entropy loss on the user inputs. So yeah, this is kind of a subtle point, but it makes a big difference when I did the fine tuning. I'm not able to get stable results with short assistant responses unless I focus the cross entropy loss on those assistant responses. So here we finally have returned a batch. The batch contains, as I said, the inputs. It contains the labels, which is what we're going to compare to cross entropy loss. And you'll notice that in order to determine where the assistant response starts, I've got this find subsequence. And the goal of this find subsequence function is to find the start of subsequence of assistant tokens. Okay, so now we have the data collator, and with that, we're able to pass it into the trainer. So I'll scroll down here past my printout of those 2 examples, and I'm going to move to the trainer, which is going to be down here. And I'll go through this trainer in a bit of detail. You'll see that I'm passing in right down here. Let's see where the data is. You'll see here, I pass in the data collator, and I pass in the train data set, and I pass in the eval data set. So this is how the trainer is going to work. But before that, we're actually not going to train all of the weights of the model. We're only going to train some of the weights of the model using a technique called LoRA. So to understand how we use LoRA, we can just take a look at this diagram. Basically, for every weight that we have in the language model, let's say it's 1,000 by 1,000 matrix, we're not going to update every weight. Instead, we're going to freeze all of these weights, and we're going to create some adapters. These adapters will be much smaller. So here, say 8 by 1,000 and then 1,000 by 8. And notice how if we take these 8 by 1,000 and 1,000 by 8, we can multiply them in a way that gives us back a 1,000 by 1,000 matrix. Now, this is called using low rank representation, and it involves updating these matrices, often set to random values initially. At least one is set to random values, the other is set to 0. So we update those during the training, which involves updating a much more coarse and simplified representation of the information in the language model, then updating everything granularly by updating every single weight. So this LoRA fine-tuning means we need way less memory, we need way less GPUs and way less time in order to do the fine-tuning. So here's how we set up LoRA. First, we print out the model to see what we need to see what matrices we want to apply LoRA to, because we also don't apply LoRA to every single matrix. We only apply it to linear layers typically. Here we have the model itself, and it's actually interesting to see the Pixtral model breakdown. There's the vision tower. This is the vision module. And then there's the language model itself, Mistral Nemo. And then connecting the vision tower with the language model is this multi-modal projector, which I said was a multi-layer perceptron consisting of a linear layer, then a Galileo activation, and then another linear layer here. So what's happening is we take the image, we pass it through the vision model. The vision model creates vectors. Those get transformed in a way to become compatible with Mistral Nemo using this multimodal projector. And then those vectors combined with the embeddings or the vectors of the text will go into the language model here. And that will produce at the end a set of predictions for what the next most likely token is going to be. And just so you can see inside this Pixtral vision tower, we have feed forward and we have attention. So that's why it's a transformer. And likewise, within the language model, we have attention and we have multi-layer perceptrons. So that's basically your feed forward and your attention. Now, as I mentioned, we're just going to train the linear layers. So anywhere you see linear here, that's what's going to get trained. We won't be training, say, the embeddings, although you can optionally train embeddings if you want. I'll show you how to do that too. That can be useful if you're going to change, say, the chat template or things like that in significant ways. It will also take a bit more memory. So to set up LoRA, which means setting up these adapters here, we're going to decide on the rank. Rank is like the number of rows. Here it's 8, but we're going to use 32. The higher, the more precision you're going to get. I recommend if you only have a few samples for fine-tuning, then probably set it at 8. If you have 100, maybe set it to 32. If you have thousands or tens of thousands, maybe set it to 128. LoRA alpha should depend on the size of the model. It speeds up the training of the LoRA adapters. That's because they are operating in a lower dimensional space, so you can afford to move faster. We're going to use rank stabilized LoRA. I talk about this if you want to check out my video on LoRA versus full fine-tuning. But essentially it means that you can use the same LoRA alpha regardless of what your OR value is, because RS LoRA will adjust your learning rate on the LoRA adapters appropriately. Now we could here in the target modules actually list out each of the modules we want to train. For example, we could put in gate projection, up projection, down projection like this here. But a quick shortcut is just to do all linear, and it will train all linear. Now, there's one other thing you can add here, which is modules to save. And you can put in a list of modules that are not linear layers that you still want to fine tune with full parameter updates. So we're not going to apply LoRA here, but we will update these modules. So for example, the typical ones you would do would be LM head. I'm actually going to do them here because I've got a larger GPU, and I'm also going to do embed tokens. So this just means that I'm going to train the embedding layers. Potentially you may decide you want to train this convolution here that generates information that basically takes 16 by 16 pixels and generates a vector. That might be worth something testing as well. For now though, I'm going to satisfy myself by training this and all the linear layers in the vision tower, the MLP projector, and in the transformer. So let's set that as okay. I'm missing a comma. And now we're going to get the PEFT model. Now we've installed PEFT above and check how many trainable parameters we have. I expect it'll be maybe 5%. That's my guess. Oh, 10%. Okay. So if you do not train these layers here, it's only going to be about 1% because LoRA is very data efficient. But if you want to fully fine tune the embedding tokens and the LM head, then that's going to mean they're fully fine tuned, which is going to take quite a bit more of trainable parameters. So anyway, we have about 1.5 billion trainable parameters out of a total of 14 billion in total. Next, we're ready to set up some arguments. So I'm going to train for 2 epochs at a constant learning rate, and I'm going to use a learning rate of 3e to the minus 5. This is probably appropriate for a model of roughly 12 to 14 billion parameters. I recommend just using a batch size of 1 if you're going to use an A40 because you'll run out of memory otherwise, and then use gradient accumulation in order to get smoothing over batches. I'm actually going to do this a little bit differently because I have more memory. I'm going to be able to afford to use a batch size of 4 for training and for eval, and I'll use gradient accumulation of 1. I only have around 30 samples, remember, so I don't want to set my batch size so it's equal to all of the data. Okay, so my learning rate is already set above. Weight decay is optional. It kind of forces the weights to be a bit smaller, which reduces overfitting. Logging steps will be every 10%. This is my output directory. Evaluation will be done every 20%. We're going to follow the learning rate schedule I've defined, which is going to be constant. And I'm going to use BF16 as true. You need to use FP16 as true if you're going to use Collab T4. And I'm going to report to TensorBoard. I'll show you how we can log that run. And I'm going to use gradient checkpointing, which reduces VRAM. You can check out my recent video there on doing Galore. It's a full fine-tuning video that explains the benefits as well of gradient checkpointing. Using reentrant will also speed up it's basically a faster variant of the gradient checkpointing. So with that, we're ready to set up the trainer. And let's see what error I have. My data collator is not defined. That's because I haven't run the cell for data collator. So let's go back up here. And I've got the training loop. And here I need to run this cell. And I think we're ready now to run the trainer. And now we're ready to run the training itself. So we'll keep an eye here on VRAM. Batch size of 4 may be too big. I think it'll be okay though. I barely fit a batch size of 1 inside an A40 with 48 gigabytes. But this looks fine. I think we're probably using more than 38, but not that much more. So here we're just going to wait for the training to run, and after that we will run the evaluation. Now in the meantime, I'm going to show you how to run TensorBoard. So let's go back to the pod, click connect. I'm going to copy this SSH command, and now you can head either into VS Code or you can head into Cursor. Let me just pull across Cursor here. So I'm going to minimize my screen, and let's click on connect to host, add new host, enter that in, add it to my config, and then click connect. So I can close this here and we should connect momentarily. There's not going to be a password. I'll just press on continue and it should load everything up. And once it's loaded, I will open up a folder. I should be able to find the workspace folder that we're working in with Jupyter Lab. So here I'll just go back. I don't actually want to go to bin, and I go to workspace and okay. And notice how we can already see there's a logs folder that's being created for the fine tuning right here. And then I'm going to click on view terminal, and then I'm going to say TensorBoard log dir logs. And what this should do is set up TensorBoard running on this port here, which I can press Command click, and now the TensorBoard is up and running. So here's my run. We can see that we have some training data available. The learning rate is here, and the training loss is here. Not a whole lot of data available just yet. And the training is just finishing up here after about 3 minutes. You see on an A100, we're actually using most of the memory here with a batch size 4. So that's why with an A40, you need to use batch size 1. That's the most you're going to be able to do. We can take a quick look at TensorBoard. Just refresh the results here. And actually, I don't think this is refreshing properly. So I'm going to just close down TensorBoard here and restart it. And then we'll open up TensorBoard in the browser. And here we go. So you can see during training, the grad norm, this is not great. It's a little bit bouncy. So potentially that indicates my learning rate is maybe a little bit too high. You can see here with training loss, it is falling. So my training is progressing. Possibly you could see I could train for a little bit longer. And if you look at the eval loss, you can see that's falling, although it's plateauing. So from an eval standpoint, it seems I've probably trained for maybe about the right amount, possibly a tiny bit too much. But yeah, I know because I ran this earlier that 2 epochs is about the right length, but you can always run for a bit longer, then go back and get an earlier checkpoint if you wanted. So we've run here now, and yeah, you can actually see here more clearly the validation loss has gone down, and it's actually gone up a little bit, which indicates we've possibly overtrained by a small amount. Next, we'll run the same evaluation that we ran earlier and see if the results are any better. Now, keep in mind, I've only got 30 data points here, 30 images I'm training on, which is not enough. But still, we should see some improvement in the performance. So here we've got a bishop and a knight. So we've got a white king and a white pawn. And half the chessboard is also visible. This is not a good interpretation. Here we have a rook and 2 bishops. So we have a black rook, a black pawn, and a white pawn. So this is actually good that it's getting 3 pieces and it's getting the right colors, and it thinks these are pawns, but they're bishops, which I suppose is not a terrible guess. And then here we have a black knight and a white rook, and half of a pawn is visible. So that's the half pawn. So this answer here is really good. So you can see we've got some improvement, although certainly not 100% accuracy, and that's why I would recommend using a bit more data. Now, at this point, I put in this line of code just so that if I do run all, it's going to stop here before pushing to hub, just allow me a chance to check the performance. You can just push the adapter to hub by running trainer.push to hub, but that will just push the adapter. We want to go a step further and actually merge. So if we want to merge the model, we should do model, and we should do merge unload. So we'll do model equals, well, we can call it merged model equals model.merge and unload. Actually, I'm just going to replace that same variable here. So hopefully that has merged our LoRA adapters, and then we'll do model.push to hub, and we'll call it trellis, chess, and we'll call it Pixtral. So this this should be enough, I think. I need to put this in inverted commas, and now we can push to hub. Now the model is going to be roughly about probably 30 gigabytes in size. So it's good that we've installed HF transfer and enabled the environment variable associated with that above. It will take a little bit of time still for this to initiate and push to hub. In the meantime, I'll show you this tool here, which allows you to do OCR. And I should mention this script here is pulled together by Hugging Face. And this part of the notebook in particular is heavily based upon a base notebook you can get from Hugging Face. And I'll provide a link to that, although there are quite a few changes now to what I've done here in fine-tuning Pixtral, because I had to modify the chat template, set up a custom data collator. So that notebook won't be very suitable for fine-tuning Pixtral, but it does include much of the code here around the OCR recognition. OCR is optical character recognition. It allows you to test if a vision model is good at reading, and it does so using these similarity scores. I'm not going to go through this in too much detail because actually my dataset doesn't have any text in it. But if you run through this, it will give you a percentage score on any dataset that does have images containing text. So I'll just mention that very briefly. In the meantime, you can see that our model is being pushed up to hub. We've got 1, 2, 3, 4, 5 different shards. And in total, that's roughly just over 26 gigabytes in size. For the next part of the video, I'm going to show you how to inference this model. So let's move right on to that. I'll now show you how to inference not just that fine-tuned model, but the base Pixtral model. And to do so, I'm going to go to one-click LLMs and pick out Pixtral. So just do Control F and Pixtral. And you can find here, just Command click, it'll open up a one-click template. Now I'm using vLLM here. All of the instructions are provided if you look at the model card on Mistral AI's repo. So you'll see you can do it, say, in a collab notebook just by copying some of this code here. But what I want to do is set up a server that I can hit as an API endpoint. So I've got a template for that ready to go, and it will run on an A40. Let's take a quick look at the template here. So we're setting the model equal to the Mistral model. Then we set the tokenizer mode to Mistral. It's basically telling it it's a different tokenizer type because it's got images coming in. We're going to limit the multimodal images per prompt to 4. That's going to allow us to fit in less VRAM. Set the max model length to 16K. And I'm going to set the port 8000 as the port we're going to hit with our requests, which means I have to expose it here. Now I've enabled HF Hub, enabled HF Transfer to speed up downloads. And yeah, just wanted to note, if we are to run our custom model, we would run here with Trellis Chess Pixtral instead. But for now, we'll just run with the base Pixtral model here. So I've started up a pod a little bit earlier. It's the Pixtral vLLM one with the settings I just showed you. Do make sure you have a volume of at least 30 gigabytes. That will be automatic if you use the one-click template. And you can check out here in the README, it has all the instructions, including a curl command for when your pod is up and running. This is going to send in a request about 2 different images, and it's just going to require you to add your pod ID here to that curl command. So I'm going to make a curl command to this pod here. Let me just find a little snippet with that curl command containing my pod ID. And let me now open up a terminal. So I'll open up a new window and paste in the curl command. Looks like my terminal is slow to initiate. Here we go. So here you can see everything is being passed in, including the pod ID. And now I'm going to press enter, and it'll take a moment and hopefully answer the second question in French. The first one, it looks like, well, I guess it's going to answer both of them in French. And here we go. So the assistant, dans cette page, une famille de 5 personnes est capturée. So yeah, it's telling us about the image, and it's telling us about the second image. So you can see everything is working well here, and you can make concurrent requests to vLLM as though it's a large language model. It works the same if you're passing in images as well. Now, in the meantime, I've set up the exact same pod, but I've done so using the Trellis Chess Pixtral model here. We can take a look at it. It's actually initializing the container. So I'll just give it a moment for that container to be fetched, and we'll see how it performs. Now, what I'm going to do is go inside this instance. Let's just test out Trellis Chess Pixtral and increase the size of the disk because I need to now store 2 different models. Oops. Click Save. And we can check the logs now here. Remember, this is the pod that I'm running with Trellis Chess Pixtral. And unfortunately right now, there isn't transformers. There isn't vLLM support via transformers for this model. And so what I need to do is convert the model from transformers back to the vLLM format. And I'm not aware just yet of scripts that are capable of doing that. So what I've done is I've just posted an issue here, Pixtral, on the Mistral community model, asking about whether it's possible to convert the model back to the vLLM Mistral format. And once it is, I'll put a note in the description of the video so that we can inference a model that we fine-tuned. In the meantime, if you do want to inference your fine-tuned model, the best way to do it is just to use the evaluation script that I've set up here in the Python notebook. You can run that in Colab. You could set up a quick, fast API endpoint using that kind of script if you want to do something naive, but that should work for now. And that's it for this video on Pixtral fine-tuning and inference. I'll put a set of links below to the Trellis resources and the public resources as well. And in the meantime, let me know in the comments of any questions. Cheers, folks.